Hello. Sorry for being a little bit late. Okay. So I think we should start now. As I mentioned last time, well, today we are going to discuss the homework last time, okay? The homework 3. And I will try to, well, do some problems with you. And then you can see, because after I read it, I really find that, well, there are something very necessary for you to understand, but well, you don't. So I think we should try to discuss a little bit more, spend a little bit more time on these exams so that you will get a better understanding of what we are going to learn very soon. And then after that, we will start to discuss about the Fourier transform on the whole space instead of on the periodic domain, which is chapter 5 of our textbook, okay, of the Stan's book. And this is the last chapter we're going to discuss well, in Stan's book. After that, we will go back to Strasbourg and then discuss something more about the PDE, pure PDE, instead of Fourier analysis. Okay? And well, before we start to discuss about the homework last time, any question? And this week's homework will be assigned on Thursday again, okay? Any question?
Wait, about which homework? About like the last one?
About the homework, you just get the feedback, okay?
Oh wait, the feedback on Sakai?
Yes, it's on Sakai, and it's well, the exercise on mainly on chapter 3. Okay. I think.
Well, I would want to hear the problem too, not the problem too, the exercise too. Like,
yeah, we are going to discuss a lot of problems, okay? And maybe then I will first discuss those problems, and if you have further questions about the problems we didn't discuss, then definitely we can try to discuss the problems you want, okay? Other than that, any question? Any question about whatever? Okay, then let's try to discuss our homework, okay? I hope from discussing this homework, you will get a better understanding about, well, how to solve an analysis problem, okay? Especially in this Fourier analysis problem. And because, well, after this homework or after this first half of today's lecture, we are going to face to another kind of problem, which is not really about this sequence stuff or this kind of uniform convergence stuff. We are going to discuss more about the convergence for an integral, for an improper integral. Okay, so it's slightly different, but still it will need those kind of idea, this kind of convergence idea. Okay, so it's very important for you to know this kind of calculations or proving in a rigorous way, which is what I want. Okay, So let's first see this problem on chapter 2, problem number 18. Okay, this problem. And this problem, he tells you that, okay, if I gave you this u equals to partial PR, partial theta, where r is greater or equal than 0, less than 1, for theta is in r. Okay, and the theta is actually in the circle, which is periodic. And then he wants you to show that first, Laplacian u equals to 0 in the disk. And the second, well, as you take the limit, r goes to 1, u r theta is equals to 0 for each theta. Okay, before we try to solve it, let me ask you a question, because I think when we discussed on chapter 3, we finally, well, chapter 2, I mean, we finally solved the problems, the well-posedness, almost the well-posedness, at least the existence and uniqueness of the Laplace, well, of the Laplace equation on the unit disk, right? And we say that, okay, as long as you have the integrable functions defined on the circle, and then you will have a unique solution to solve the problem. However, it turns out that this exercise gives you an example. This example is very interesting, and it said that, okay, this kind of function, solve the problems Laplacian equals to 0, and when you take the limit, it's equals to 0. Which means, since Laplace equation is a linear equation, we can somehow add this solution to an arbitrary solution. And this function is obviously is not 0. So does that mean that our problems, Laplace u equals to 0, u on the unit circle equals to f theta, does that mean this kind of problem is not well posed? Or does that mean that we don't really have the unique solution, as we proved before? What does this mean? What does this problem mean? What does this problem mean? Because I think we said that we just gave the remark when we try to discuss about the theorems. The theorem says that, okay, if you have Laplace u equals to 0 and you want to find a solution such that Laplace u equals to 0 and u tends to f on the boundary of this disk, unit disk, and it seems that we have a unique solution, right? We prove that as long as your f is integrable, then, well, maybe as long as your f is continuous, then you will have a unique solution. Okay. We say that when we prove this kind of theorems, which is theorems, I forgot the number of the theorems in our textbook, the last theorem on chapter 2, we prove that this system has a unique solution. Then why we can find another thing such that this kind of thing, if we add it to our unique solution, we get another solution. Why?
Because in the second property, the limit is 0 for each theta. This is something like pointwise thing.
Exactly. That's very good, because this should be the correct answer. Well, you can look at the second property and try to compare the corresponding properties for our PDE system. Okay, for our PDE system, the theorem states like this. Well, if you want to find such kind of u so that Laplace u equals to 0 in the disk and u tends to f uniformly on the boundary as r goes to 1, then such kind of u is unique. Okay, so if you add this kind of U, then the convergence becomes pointwise convergence. It will not be a uniform convergence, which is why this kind of functions will not rule over uniqueness of the solution. Okay, it will not come to our unique solution and generate another solution. Okay, this is a very important point, because that means if you release this kind of uniform convergence a little bit, even if it becomes a pointwise convergence, then at least you cannot discuss about the uniqueness of the solution, right? This gives you an example. You say that, well, if you only want a pointwise convergence, then the solution may not be unique. Okay? So this also gives us a very important warning about when you try to solve this problem, you should be careful. Okay? What you should be careful is, well, since you try to discuss something without a uniform convergent, or it might not be it may not converge uniformly, then if you try to solve something, or if you try to do some calculation of something, you must be very careful. You cannot do it formally. Formally, I mean, you cannot do it term by term. Okay? So this is why, well, most of you did something wrong when you try to prove this problem. Okay? For instance, for the first part, it's very easy to check actually if you try to check it formally, because you are able to find the Fourier expansion, or this trigonometry, well, this trigonometry expansion of this U, because you know what is the expansion of PR. PR is just the summation of R to the power n and e to the I n theta. Okay, and you will see that if you take partial theta of this kind of thing, and then what you will get is this kind of, well, the summation of In, because you take partial theta, so you should bring down this In in front, and R to the power n, e to the In theta. Okay? Then, if you try to find whether it is a solution or not to this Laplace equation, then yes, you can definitely check whether you plug in U, it is a solution or not, which means partial R squared U plus 1 over R partial R U plus 1 over R squared partial theta squared U equals to 0 or not. Okay? You could try to plug in them term by term, which will give you, okay, partial R squared, well, partial twice this R, it will give you In times n minus 1 times your R to the power n minus 2, right? And e to the In theta, and this terms, it will give you something like similar things, In times n times, well, R to the power n minus 2, e to the In theta for the single term, and this term, it will give you, okay, In times In squared, right? And times R to the power n, e to the n minus 2, In theta. Okay, if you sum them up, you'll find that, okay, basically you will get 0.
Wait, can I ask a question? Sorry, I missed the part. When did we say that PR is the sum of Rn E In to the, like, how do we know that again?
Because this is a definition of our, well, Poisson kernel, right? Our Poisson kernel is what? Our Poisson kernel is theta R how can we compute our Poisson kernel? Well, that is, we try to compute it by saying that, okay, the Abel summation, the Abel means of summation of the Fourier coefficient of f is f convolved with PR theta r, right? So the Abel sum of Fourier series of f is, well, the summation of r to the power n and e to the I n theta a n. Okay? Am I right? And then you want to write it as, you want to write it as this some f convolved with PR. And then you want to compute what is your PR. Okay, so let's try to write it as some convolution form. It's r to the power n, e to the I n theta, and this a n is f hat n, which is the integral 1 over 2 pi from minus pi to pi, f theta e to the minus I n theta. Well, maybe let's not use theta because we already use theta. Let's use eta here. Eta d eta. Okay, so we want to write it as an integral, as a convolution. Then what is this? This is, we put everything inside of integration. It's 1 over 2 pi, as well as this integral, the summation in n. Okay, and r to the power n times e to the, this is I n theta minus eta f eta d eta. Okay, so which is why if we want to call this part a kernel, okay, if we want to use it as a kernel, then this kernel, we should define it as, a summation of n r to the power n e to the I n theta. So that you can see that this thing, f convolved with PR is equals to the summation r to the power n e to the I n theta and f hat of n. Okay, we can define this PR theta this way. So this is your PR theta. Okay, so if this is your PR theta, then of course, if you try to take the derivative and plug in, then you find that eventually you got 0. Term by term, okay? Term by term. This is very dangerous when you try to do something, at least in analysis, when you try to do something term by term. Because the problem is, as we mentioned before, if you want to take derivative of your functions term by term, like fx is equals to something like fnx, okay? And if you want to compute partial square over partial r square of your fx, then you say that, okay, then for instance, if you want to take partial x square of fx, is that equals to partial x square of fnx? Well, it's much easier to compute if that is true, right? Because then you only need to compute this derivative of each term. You only need to compute the derivative of each term and take the summation. If the derivative of each term and you take the summation is just a 0, then yeah, maybe you should get it equals to 0, right? However, well, this is a very dangerous operation, as I mentioned. Well, in the future, if you try to do something like, well, if you try to study engineer or something similar, then you could try to play with this kind of infinite series in this way, because maybe you don't really need any rigorous, analysis in engineer. You can just do everything formally. However, since you are a math major, I have to warn you this. If you want to do this kind of operation, you have to check, okay? You have to check you are able to do it this way. This is very important as a math major student. So I said that you have to check. What do you need to check? What do you need to check?
Wait, you mean that we have to check the uniform convergence and stuff like
Exactly.
that?
Exactly. So if you want to do it this way, which means you try to switch the order of the summation, infinite summation, and the derivative, okay? Then if you want to do this kind of operation, you have to check, okay? Because, well, why I say it's change the order of this derivative and the summation is simply because, well, if fx equals to this one, then the derivative of fx is of course equals to the derivative of the summation. That's true. But then if you want to go from this step to this step, you simply swap the order of derivative and the summation. Okay? So if you want to switch the order of these two operations, you have to check that this summation you write is uniform convergent. Otherwise, you cannot say this is true. Okay? This is very important. The reason is very simple, although we don't really need this kind of reason in our course, but the reason is very important and simple. It might be needed when you learn 308, the real analysis. It's simply because this summation, you take one limit, okay? And this derivative is another limit operation. It's another operation involving limit, okay? So if you try to switch these two operations order, then you basically change the order of taking limit. This is something serious, and it may not be true. It may not always be true. It's just like, I think you may have a better impression on this. It's just like when you try to have a function, then in 202, in calculus 2, well, you learn that if you first take derivative in x, and then take derivative in y, it may not equal to if you first take derivative in y and then take derivative in x. Of course, if f is smooth enough, then these two are equal to each other. In our course, we assume, well, this function is smooth enough, so it's always this one equals to this one. However, if we don't assume anything about this function, then we cannot say that you can switch these two operations order. The reason is just very simple, is because you are switching the order of the limit operation. And this might be something serious when you try to switch the operation of the order of the operation of limit. Okay, it may have some problem on it. Okay, which means, well, if you are going to say, since term by term is just a 0, right? Term by term is just a 0. You will have to say that, okay, this sequence, this summation, it converge uniformly to a function. Okay? We want to show this Laplace u equals to 0 in the disk or in r is greater or equal than 0, less than 1, theta is in r. If we want to show this, you know well, of course, if you know the expression of u by a closed form, not as an infinite series, you can check that. That's definitely true. Okay, you can just do the calculation. The calculation is a little bit too much, yeah. Of course, it's not really, but it's a little bit too much. But of course, if you try to do it that way, then you find that, okay, it's true. Okay? Otherwise, if you try to use the infinite series to show this is true, then you have to show that some uniform convergence. Okay? This u is equals to in times r to the power n e to the in theta. Okay? We want to show some kind of uniform convergence of this sequence. Uniform in two variables, r and theta, so that you can take derivative both in r and theta. Okay? However, the bad thing is, well, you may find that this sequence, it converge, but it seems not to be uniform convergent, at least on this open or half-open interval for R, right? Because when R tends to 1, this sequence is very bad. If R is less than 1, then it's good enough because you can see that this part is uniform. Well, it's actually geometric series. And this part is just a linear in n, right? So of course, this part, this total thing will be very, very small, will decay very, very fast. That's only when R is not equal to 1, okay? But when R is very close to 1, at least we do not have any upper bound to say that this kind of sequence is uniform convergent, okay? Well, still remember, the only way we are able to use, at least, well, the only way that is necessary for this course is if you want to show this function converge uniformly, then you only need to show that Fn is bounded about by some Bn, and Bn is, it converge. Okay, then we can show that this sequence, it converge uniformly. This is the only thing you need. And it's the only way in this course that is necessary to be able to do, to be able to, well, prove everything. Okay, so you only need to find an upper bound for this kind of thing so that it converge. But if R is very close to 1, well, if you try to compute the norm of this kind of functions, it's actually equals to n times r to the power n, right? So when r is very, very close to n, there is no upper bound such that it becomes something summable. It will become something like n, but n is not summable. Of course, it will diverge. Then how could we solve this contradiction? How can we find some better estimate of this? This will be the problem, right? How can we show this kind of thing converge in some way uniformly so that we know this Laplace u is equals to 0 by taking this derivative term by term. How can we do that? Any idea? Any idea? Well, the idea here is actually similar to what we try to do when we try to solve the problems on the unit disk, okay? Which is, we don't really know whether this kind of sequence converge to this function u uniformly or not on this domain, okay? Actually, it's not. It will not converge uniformly on this domain. It's just like this kind of sequence, like x to the power n, is not uniform convergent to x, to this 1 over 1 minus x on this minus 1 to 1 uniformly, okay? Not uniformly on this part. Not uniformly when x is very close to 1. But what we do know is it may not converge uniformly on this kind of thing, on this kind of interval, but it converge uniformly on any sub-closed interval, okay? It will converge uniformly on any closed subinterval of from 0 to 1 in R. Why is that? Well, it's just very it's very intuitive, simply because if you have any subinterval, closed subinterval of 0, 1, then that means, okay, you must have an upper bound of this closed interval, right? Closed subinterval. So for instance, it might be 0 to 0. Okay, so which means on this closed subinterval, you always have R is less than 0. Okay, so in this case, you know that in R to the power n e to the in theta is less than n times rho to the power n. And you can actually show that the summation of n rho to the power n is less than infinity. Now, rho is a fixed number. It could be 0.9 or 0.99 or 0.9999. Okay? So as long as you give me an R, for any R that is in this open interval, okay, there exists some kind of rho such that this rho is between R and 1. Okay, because R is in this interval, it cannot be 1. So of course, between R and 1, there is another number. Okay, and what we do know is this series converge uniformly not 0, 1, but 0 to 0, closed interval. Okay, so that means, okay, at R, at the point R, you are able to take derivative term by term. Okay, that means this is valid. or partial r squared plus 1 over r partial r plus 1 over r squared partial theta acting on u is equals to, you now can switch or you can change the order of these two operations, the summation in n and this operator acting on term by term. This is in times r to the power n e to the in theta. Okay, which equals to 0 at r. Okay, at r. So which means since r is arbitrary between 0 and 1, so we know that. So that means Laplace u equals to 0 for any r between 0 and 1. Remember, again, remember, this Laplacian u equals to 0 is local. Okay, it's just a local. So which means we only need to show, if we want to show Laplace u equals to 0, we only need to show for any given r and theta, Laplace of u at this r at this theta equals to 0. Okay, so this Laplace u equals to 0 as long as you gave me an r and you gave me a theta. Okay, because we can do it at this given r, we can do the derivative term by term of this kind of expansion of u. Okay, so we got Laplace u equals to 0 in the disk. Okay. Any question?
Just too many of them.
So yeah, try to think about, well, what we just explained. Okay, what kind of thing we try, what is the logic of this problem? Okay.
Could you explain like what's the difference between locally and globally?
Well, locally and globally, this is something which is kind of hard to explain because they are just some concept. Okay, there is no very explicit definition of local and global. It's just something that you try to understand everything. For instance, if you try to say this kind of sequence converge uniformly, then this may be seen as something globally. Okay, some interval it converges uniformly. That somehow means at each point of this interval it will converge, and it has some very good properties. It will have some relation. This convergence has some relation point to point. Okay, so this is something more or less like a global stuff. Or if you try to take the integral of a function, then this is also something global stuff, right? This is also something global because it will depend on every point of this interval. So this is something like global stuff. But local stuff is just, you look at one point, okay? You just look at one point and see what happens at this point, not any other point. Okay, you're just interested on this r and this theta, not something for all the r and all the theta. You are just interested in this particular one r and one theta. So which is why we call it local property. Okay, because it's really just one point on your domain. Okay, but of course, this is just a relatively explanation of local and global. Well, this is just something that is not very explicit, as I mentioned before. So here, it just trying to tell you this fact. This kind of convergence is a global proposition, whether this convergence is uniform or not. It's a global proposition, but Laplace equals to 0 or the derivative equals to 0 is just about each single point. Okay, it's not about whether it is global A equals to 0 or not. It's just about one single point.
Okay, I see. Thank you.
Any other question? Okay, and for problem number B, it just say that, well, the limit of your functions for each theta, it equals to 0. Well, this is very easy to calculate. You can just, well, now you don't really need the expansion of your u, okay? You just need to use this kind of expansion, write it as a closed form, BR equals to 1 minus R squared over 1 minus 2 cosine theta R plus R squared. This is your PR. You really take the derivative on theta, right? Partial P, partial theta. I think it's 1 minus R squared times some sine theta, blah, 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 and something. And then you just need to fix theta and take the limit as R goes to 1. And if theta, you can see that if theta equals to 0, then this total thing is just a 0. If it is not equal to 0, you can just plug in because, well, the denominator is not equal to 0. And then you got that. This part is very easy. Okay, it's just problems in calculus 1. Okay. This is about exercise number 18. Any question?
Can we just like use a polar like coordinates to solve for the first problem?
Yes, you definitely could, which is you try to plug in PR, right? And then try to compute what is Laplace U, right? You already know what is U. U is a closed form. You have a closed form for U, which means you don't really have a series. Of course, that is just a very complicated function. And then you can take the derivative. That's totally correct. I'm not saying you cannot do it like that. It's just because a lot of you just do the expansion and try to compute it term by term. So this is why I try to explain it to you that if you try to compute it term by term, you have to be careful. Okay? Of course, if you plug in PR equals to this one, and then plug into this Laplace U by using this form of PR, then of course you can get, okay, it's equals to 0. Okay, and that's correct.
So like in this case, we don't have the problem of like.
No, you don't, because you only have finite term. You only have one term. Okay.
Oh, I see. Thank you.
You don't need to worry about that if you try to do it that way.
Thank you.
Any other question? Okay, the next problem I would like to discuss is problem number 20. For problem number 20, something similar happens, okay? Something very similar to these problems happens, and again, you should be careful when you try to do this kind of thing, okay? That is, you have still the Laplace equation, but now it's not on the unit disk. It's on the annulus, which is the punched disk, right? The truncated disk. And U1 theta equals to F theta, U rho theta equals to G theta, which means your domain looks like a donut. Okay, this is your domain. So for this domain, you have two boundaries, and then you have to give me two boundary conditions. One is this one, another one is this one, so you have F and G. And then he said that, okay, I gave you, well, you can solve it similar to our process, try to do the separation of variables and try to match these two boundary conditions, and eventually you formally get the solution. The solution should somehow looks like this. And it's not equals to 0, 1 over rho minus rho to the power n minus rho to the minus n. after you match all the coefficients, this one is rho over r to the power n minus r over rho to the power n times an, where f theta has a Fourier expansion like an e to the in theta, g theta has a Fourier expansion like bn e to the in theta. Okay, plus r to the power n minus r to the power minus n bn times e to the in theta. Okay, plus a0 plus b0 minus a0 and log r over log rho. Then he asks you, okay, we formally solve this problem. That's totally fine. He just show you how to solve this problem formally. Again, formally. How to solve this problem formally by separation of variables. Writing u as a summation of un, and un can be written as something only depends on r, something only depends on theta. Then after you match all the coefficients, you get this kind of form as your solution. Okay? Then he asks you, okay, how you can show that actually this solution is really the solution and match the initial, well, the boundary condition, which is probably you should try to show, at least try to show that Laplace of this u equals to 0, but the problem didn't ask you to show that, so it's fine, but you can see that after all, we can show that. It's very easy to show that. And then, at least for this problem, he asks you to show, okay, for your expression, ur theta, it subtract br convolve with f, evaluate as theta, it tends to 0 as r goes to 1. Uniformly in theta. Okay, and you can actually find that it's actually not uniformly in theta, but also uniformly in r. Okay, and ur theta, this is the matching of one boundary condition. Okay, you analytically or rigorously show that they are the same. And then you show that you want to show that this formal solution also match another boundary condition. Okay, again, this solution you write, it's just a formal solution. You just solve everything formally. You just say that formally means, well, you just say that if it is a solution, then it must match in this way. And the coefficient must equals to this. But you don't show it is actually a sufficient condition. It is sufficiently to be the solution. Okay? And this one minus p rho over r. Convolve with g theta tends to 0 as r goes to rho. Uniformly in theta. Okay? He wants you to show this is a solution that makes sense, which means it should satisfy the Laplace equation, which is something he didn't ask you to show because, well, basically you are doing something similar to this one. Okay? Meanwhile, it also can be done that this function will satisfy your boundary condition. It satisfies your boundary condition simply means if you plug in r equals to 1 and r equals to rho, it must be equals to f and g correspondingly. Okay, and this is a way how to show this is true. Because you can show that, you can see that when r goes to 1, then this is a Bell sum of the Fourier series of f theta. As long as f is continuous, which is problem gives you, this one will converge to f uniformly. So this converge uniformly means ur theta converge to f theta as r goes to 1 uniformly. And this one just say that ur theta will converge to g uniformly as r goes to rho. Okay? So he asks you to show that this formal solution is indeed the solution. He asks you to show it rigorously. So again, well, for this problem, if you try to see it very roughly, then you'll find that, okay, of course, this must be true, right? Because if you plug in r equals to 1, this term simply disappears, right? R equals to 1, this can cancel this denominator. What you will get is an times e to the in theta plus a0. This term disappears because r equals to 1, right? So of course, if r equals to 1 and you plug in, this exactly equals to the Fourier expansion of f. So it seems to be trivial. And if you plug in r equals to rho, then you get, okay, this equals to this. And this will cancel this one. So you have bn times e to the in theta and not equals to 0. And this will give you 1. So it's b0 minus a0 plus a0. So it is exactly the Fourier expansion of g. Yeah, so of course it must be true. So can we do it like that? Can we do it like that?
You need to check its converges uniformly.
Yes, we have to check. Well, what did we do? What did we do if we try to plug in?
Switch the order of summation and limit.
Exactly. So if we want to plug in, if we just want to plug in, then yes, you could say that, okay, you can just plug in them term by term, right? So if you have f, say f1, then by definition, it is equals to fn of 1, okay? This is fine. But now what you're trying to do here is not f, you evaluate at 1, but you take the limit, you see, as r goes to 1, as r goes to 0. You take the limit as x turns to 1 fx. Okay, suppose fx equals to the summation of fnx. You try to take the limit of fx, which is you try to take the limit as x goes to 1, the summation of fn of x. Okay? And if you want to switch, if you want to plug in and say this equals to each other term by term, then you are trying to say whether you are able to switch the order of these two operations. And since each terms is each terms is just a continuous, so of course it's equals to fn of 1. Okay, but this step is something very suspicious, because if you really want to switch the order of these two operations, you will have to change these two operations, and these two operations are both operations involving limit. Okay, which is something very dangerous when you try to check. If you want to check that, that's totally fine. But if you want to check it this way, that's totally fine. But you again have to show that this convergent, it will converge uniformly, so that you can somehow ignore this kind of limit. This limit is a very strong limit, so that you don't really need to worry about it. This is the meaning of uniform convergence, so that you can switch this limit and some other limit operation. It's simply because you have a stronger limit, which is a uniform convergent, as your backup. Okay, as something, well, something can help you. Okay. So this is something I believe you will need to practice again and again, at least in 308. And this is very important in analysis, especially in PDE, because you will find that eventually what you're trying to solve, if you want to solve a PDE explicitly, what you're trying to do is you always try to expand it. You always try to do some expansion of the solution and try to solve it formally. But then if you really want to solve that PDE, what you're trying to do is you have to show that the formal solution that you expand is really indeed a solution. Okay, which means you want to show some convergent, some uniform convergent of your sequence, of your expansion. So question?
Professor, I just want to make sure that like if a series is finite, so we can always switch the order, right? We don't
Exactly. Yeah, you are right. Because if this series is finite, then you don't need to take the limit when you try to take the summation, right? But if it's infinite, then you will take the limit, right? This is a different.
What if there are cases like because as we are learning in a L2 space or something like if there is a series like from -infinity to infinity, but there are infinite zeros in it. Like
yes, in that case, it's only finite term. In that case, it's only finite term. And you can also say that actually, well, if you have infinite many zero, then it's either finite terms problems, or you can also say that, okay, it is actually a uniform convergent, right? If you have something like Fn equals to 0 when n is bigger or equal than n, then we must know that, okay, all this kind of, smaller n, your Fn is bounded above, right? It's bounded above. And of course, well, if n is less than n, and Fn is equals to 0 when n is greater or equal than n. So you know that this kind of sequence B, and you have capital N's B and 0, 0, you have infinite 0. This sequence is, it's a convergent sequence. It's a summable sequence, right? So it still converge uniformly. Okay. Any other question? So this is something you have to be careful, okay, when you try to solve a PDE problem.
Oh, can I ask a question?
Of course.
So, say for example, we have a PDE, right? And so we found like the stuff, and now we want to know it's uniformly convergent, right? And so, what do we usually do to prove it's uniformly? Because like, we have a couple of theorems showing that something is uniformly convergent, but like, do we just use them, or do we show it just like directly trying to get like nice bounds, or what do we in generally do?
Well, in general, this would be a very hard problem. Otherwise, we cannot, otherwise the PDE problem will become pretty easy if you have a general criteria. In general, this will be a really hard problem. At least in our course, all the problems will be this kind of problems. As long as you, if you want to show something converge uniformly, you will always have an upper bound, and this upper bound is summable. Okay, in our course, it's always like this. In general, this will be an extremely hard problem because for different problems, you will have different idea. Okay, and sometimes you don't even have a good idea, so that the problem becomes unsolvable. Okay. Any other question? Okay, so for this,
I have a question.
Of course.
Can you repeat how we get the uniformly convergence?
Of course, yeah. So at least in this course, or in the, in most of the situations, in analysis. What you're trying to do is you're trying to get uniform convergence simply by the upper bound, okay? If you want to show this Fn of x converge uniformly, you just want to show that Fn of x is bounded above by some functions, or I mean by some constant that depends on n, okay? And the summation of Bn is finite, which means you fx when Fnx when n is very big, then these functions may oscillate a lot, but the total oscillation of Fnx when n is very big is super small. It's neglectable. You can ignore them, okay? Because this kind of sequence is summable, so when n is very big, then this kind of sequence is very small. Bn is very small. So that means your Fnx when n is very big is uniformly small. Although it may oscillate, but the oscillation is very, very small. Okay, then we can conclude that this Fn of x is converge uniformly. Okay.
Okay.
Yeah, this is a very useful way.
And I have another question.
Sure.
In this problem, what does SR goes to 1 uniformly in theta and SR goes to rho uniformly in theta mean? The uniformly here.
This uniformly simply means, okay, it's actually the same thing, which is you want to say that, well, from epsilon delta language, it just means you are this uniformly is actually abbreviation. It's just a thing. It's saying that uniformly in x. Okay, which means this convergent, your x may oscillate. There might be some fluctuation of x, but this kind of fluctuation of x is neglectable. You can ignore that. Here, u r theta minus p r convolved with f, theta tends to 0 uniformly in theta or maybe in r as well. It just means that, okay, your theta may change, but this kind of convergent, it will not change. So in the language of epsilon delta, that simply means for any epsilon greater than 0, okay, and let's say r fixed, because we didn't discuss this r, but eventually we'll find that actually you don't need to worry about r as well. For any epsilon greater than 0, this function minus PR convolved with f theta, this minus this function, because this kind of function have two index or two variables, r and theta. Okay, so which means, well, you want to take r goes to 1, that means you want to take some kind of index goes to 1. For this one, this r goes to 1 is somehow similar to this kind of, you have the partial sum of your Fn and you let n goes to infinity. Okay, n goes to infinity is same here to be r goes to 1. Okay, so that means, this means for any epsilon, maybe I shouldn't say r is fixed, for any epsilon, because this r, it takes the place of capital N, okay? For any epsilon greater than 0, there exists some delta such that you take this r goes to 1, you take this n goes to infinity, 1 minus r is less than delta, implies this function minus this function is less than or minus 0, it tends to 0, right? This function minus this function is less than epsilon. as long as you have 1 minus r is less than delta, these two functions difference is less than epsilon. Okay. So you can somehow will understand it in the sense of this kind of summation. It just means this converge to a function, say fx, uniformly in x. This simply means for any epsilon greater than 0, okay, there exists some capital N, N0, which is the same stage, where it's the same place as this delta. N0 can be seen as some kind of domain near the infinity, okay, such that n is greater than n0. As long as you have n is greater than n0, your n is big enough, the summation of n less or equal than capital M, fn of x minus fx is less or equal than, is less than epsilon. Okay, so which means if n is close enough to infinity, then the difference of these two functions is very small. Doesn't depend on x. For any x you gave me, it will uniformly very small. Okay, here if r and 1 are very close, then these two functions are very close, no matter what theta you gave me. This is the meaning of uniformly in theta. Okay, so this is how you can understand this kind of uniform convergent, either for some kind of index that's not an integer index or the integer index. They are basically the same. Okay, they are basically the same. Is that clear?
Yes, thank you.
Mm-hmm. So it just to say that, well, this kind of convergent, it doesn't depend on your theta. So which means theta is something not relevant, which is why we call it uniform. Okay, uniform converge. So now the problem is how we can solve this problem, right? With this u, with such kind of u, how we can show that this u, when r tends to 1, it comes to something like f. Okay, this would be the problem. And well, let's try to see this kind of problem. Let's try to solve this kind of problems just similarly as we did before. Okay, but this may need some kind of trick, may need some kind of estimate about the terms, which is something very necessary when you try to do some estimate. Okay, for instance, let's say, well, these two actually they are somehow somehow similar. Okay, when r tends to 1 or r tends to 0, they are similar. So I will just do one, for instance, this one, and the other one I will leave you as well, good exercise. You just replace this kind of r tends to 1 to r tends to 0 by replacing r to be something like rho over r. Okay, then you can see why I say they are actually, well, I think it's r over rho. Then you can see why I say they are kind of similar. Okay, let's try to do this one. Of course, if you still have any questions about, well, how to get r tends to rho's result by using r tends to 1, you can still ask me. Okay, I can still tell you how you can do that. So when r tends to 1, that means r is very close to 1. Okay, if r is very close to 1, then that means rho over r to power n minus r over rho to power n. This r is very close to 1, so it's very far away from rho, right? So this kind of thing is basically, it's almost like rho to the power n minus rho to the power minus n. Okay? So for this kind of thing, it's not very bad. So which is why I'm saying that they are somehow, these two guys are somehow similar for r tends to 1 and r tends to 0. Okay? So here, let's try to use this kind of estimate to play with it. You have this term and this term correspondingly. Okay? So let's try to write them and see what we can say about this kind of corresponding terms. Okay? So this is r to the power n, r to the power minus n, divided by rho to the power minus n minus rho to the power n. The reason I switch these two is simply because both r and rho are less than 1. So I just want to write everything to be positive. This term is bigger than this term, and this term is bigger than this term. Okay? So I write everything positive, both top and bottom are positive. Okay? This is the term in front of b. And correspondingly, you have the corresponding terms in front of a, which is r over rho to the power n. Now you can see that r is bigger than rho. So this is a number bigger than 1, okay? Minus rho over r to the power n. And this is a number smaller than 1. And this is bigger than this. Divide by rho to the power minus n minus rho to the power n. These are two coefficients in front of an and bn, and so that we can play with, so that it can help us to show that, okay, the norm of them is less or equal than something that's summable. Okay, this is our hope. Then how can we do some estimate of these two terms? Well, what you can say is, this is somehow tricky, but what you can say is, well, this term, since these two guys are very small and these two guys are very small, you can actually show it's less or equal than r to the power n over rho to the power minus r to the power minus n over rho to the power minus n, and this can be shown that it's less or equal than r over rho to the power n divided by rho to the power minus n. Why is that? Well, it's simply because if you multiply r to the power n divided by rho to the power n both sides, and you'll find here is 1 minus r to the power 2n, here is 1 minus rho to the power 2n. And 1 minus r to the power 2n is definitely smaller than 1 minus rho to the power 2n because r is greater. R is some bigger number. Okay, so 1 minus r to some power is less than 1 minus rho to some power, which is why I'm saying this is true, so that this is true. Okay, and this term is just rho over r to the power n, and this term is just r to the power n. Okay, is that clear? Now you can imagine this this kind of inequality must be true. Okay, this is not a unique way to show it. I just think this kind of way may be easier to understand. Okay, and it makes it looks a little bit better. Okay, and then you find that, okay, these two guys, when r is very close to 1, what we do know is this term is very good, right? This term is actually something less than 1, right? You know that when r is close to 1, rho over r is close to rho. Okay, so you can say that, okay, when r is close to 1, then rho over r, let's say, is well, it's less than a half rho. I cannot say it's half rho, but well, I can say it's something like rho to the power. How could I name it? Let's say r is well. Well, let's say it's square root of rho. Okay, it doesn't matter. We can just by some intuition say that this rho over r is just some kind of some function of rho, which is still something less than 1. Okay, it could be rho to some power like a half. It could be something like rho multiplied by something like 2, for instance, or something like so that this kind of thing is still less than 1. Okay, this could be true simply because we can choose r to be close to 1 and r close enough to 1 so that r is greater than square root of rho. Okay, then of course this inequality is true. So that means rho over r to the power n is less than square root of rho to the power n. And the summation of square root of rho to the power n is less than infinity. Okay? That okay? So that means this kind of terms are good terms. That means the summation of r to the power n minus r to the power minus n rho to the power n minus rho to the power minus n bn e to the in theta, this part of your sequence converge uniformly. Because you have this kind of upper bound to bound this part. Okay, and Bn is just something bounded above because it's a Fourier coefficient. So you know that this part of your solution converge uniformly. So if you want to take the limit as r goes to 1, you can plug in term by term. Okay, so limit as r goes to 1, this r to the power n minus r to the power minus n, rho to the power n minus rho to the power minus n, bn e to the in theta is equals to the sum of the limit as r goes to 1, r to the n minus r to the minus n, divide rho to the n minus rho to the minus n, bn e to the in theta, which equals to 0. Okay. So is that clear? So when r goes to 1, this the second term of your expression is a good term. It converges uniformly simply by this kind of estimation. That okay? Well, you may find this kind of estimation may be hard to try to imagine or try to write it down. And I agree, because this problem is not as easy. Which is why this kind of problem is always worth to think about. Okay, and get this kind of intuition is very important. You try to show it is somehow bounded above. So how can you find the upper bound? This would be something very interesting. This would be something very interesting, and is something really needs you to think about. Okay. Then the rest of the problem would be, how about this first term? How can we show the first term is also something we can plug in? Well, the first term, if you want to plug in, then you have to show it converges uniformly. But it seems that this kind of bound is a really good bound. It's r to the power n. It's a really good bound. So if we do not have any other idea, then maybe this is the best bound we can get, right? And then we cannot show it converge uniformly. Then the problems just gives us a hint, right? It wants us not to show that, well, this UR theta tends to F theta. Instead, he wants us to show this UR theta minus PR convolute with F tends to 0. So maybe if we try to write F theta instead of F theta, but PR convolute with F theta, the problem may becomes easier. What is PR convolute with theta? Convolute with F? Well, as we mentioned before, it is the summation of R to the power N. Well, AN is a Fourier coefficient, Fourier expansion of your F, e to the I n theta. Okay, we can write this as an equation because for any R is less than 1, this always converges uniformly. So we can write it as an equation. Okay, so then you want to show the difference between these two functions tends to 0. So let's try to write the difference of these two terms. Okay, the difference of these two terms, well, it's just an addition, so that you can just combine the terms. You can just combine them term by term. Okay, so the addition does not involve any limit operation. It's just the sum when n is not equals to 0. We just write the first part. Okay, it's 1. Well, it's r rho over r to the power. Let's write it in the way we write before, which is try to switch these two terms. R over rho to the power n minus rho over r to the power n. Okay, divide rho to the power minus n minus rho to the power n, an e to the I n theta, minus, okay, this guy, r to the power n, an e to the I n theta. Okay, plus the rest of the terms, plus something else. This something else, we already get the estimation. It converts uniformly, so we don't need to worry about it. So the only thing that might be important is this part. Okay, and for this part, it's just something not so bad. We can combine these two terms and write it as r over rho to the power n minus rho over r to the power n, divide by rho to the power minus n minus rho to the power n, minus r to the power n. So we use a common denominator, minus r to the power n times rho to the power minus n, plus r to the power n rho to the power n, times an e to the I n theta, right? Plus some other terms that we're already able to deal with. Okay, that's good enough. These two terms cancel. Okay, so that means it's equals to, well, n is not equals to 0. This is r to the power n rho to the power n minus rho to the power n r to the power minus n, divided by rho to the power minus n minus rho to the power n, an e to the I n theta plus something else. We want to show, if you want to show this tends to 0 uniformly, you just want to get some estimate of this kind of thing, right? Of this part. So again, which means you will need to get an estimate of this part. If we can get something which converge, well, absolutely, or which is something like, some geometric series, then we are done, right? So what is Rn rho to the power n minus rho to the power n r to the minus n divided by rho to the power minus n minus rho to the power n? How can we do an estimate of this term? Well, it's not so bad. We can take out rho to the power n, right? And inside part is rho to the power minus n minus rho to the power n. And on the top is r to the power n minus r to the power minus. So you can actually take out this absolute value and write it as r to the power minus n minus r to the power n divided by rho to the power minus n minus rho to the power n, which is something we have done before, right? Less or equal than rho to the power n times r to the power minus n divided by rho to the power minus n, rho to the power n over r to the power n. So it's rho to the power n, rho to the power n over r to the power n. R is less than 1, right? R is very close to 1. So again, it's less or equal than rho to the power n, something like square root of rho to the power n, which is like rho to the power 3/2 to the power n, which converge uniformly. well, I mean, which converge absolutely, which is summable, okay? So this sequence, r to the power n, rho to the power n, minus r to the power minus n, rho to the power n, rho to the power minus n, minus rho to the power n, a n e to the I n theta, converge uniformly in theta, okay? So we can, if we want to take the limit, you can just plug in r equals to 1, and we got what we want. I'm not writing. Okay? So it just, for this problem itself, it's not very hard. It just asks you to look at this kind of observation. Of course, if you do not have this kind of observation, then you still get some intuition, okay, how we can do some control or do some kind of algebra so that these terms become something geometric. Okay, so this is the key part of this problem. And as long as you have this kind of thing, can be bounded about by some geometric series, then you are done. Okay, then this problem are done. So this is how, so again, for this kind of problem, the key part is still the idea, or it's the key part is still, well, how you can think about this problem or how you should think about this problem in order to solve it. Okay. Any question about this problem? Any question?
Like after we prove the uniform convergence of the series, and we like plug r equals to 1 into it, and what we get is like U is a series, is a Fourier series of f of theta, and it means that f is like f converges to its Fourier series as like
well, be careful about this. I'm not saying that this you can plug in at very beginning. Okay, I'm not saying that this converge uniformly when r goes to 1. I'm not saying that. What I'm saying here is u theta minus pr convolute with f will converge to 0 uniformly. So here, if you plug in, you try to plug in here. You try to plug in here. And if you plug in here, you find that it's actually equals to 0. Okay? It's not some sum of the Fourier expansion of f. Be careful.
I understand it. Thank you.
So here, if we plug in, we find that it tends to 0 instead of something else. Any other question? Any other question? Well, if no, then let's have a short break and we'll resume at 39, okay? Okay, so let's start and discuss more about our homework problem, okay? And after this, what I'm going to discuss is problem number 2 of chapter 3. Okay, chapter 3, number 2, which is a problem he asks you to show that little L2 space is complete. Again, I think all of you did quite good in the sense of, well, trying to use some tricks to deal with something. But the key part or the key problem for your homework is, well, you don't really get the correct idea in order to write the correct proof or rigorous proof in analysis. This would be very important for you, okay? You're taking this course, and this course is actually an advanced analysis course. So you will need to know a little bit more about analysis, at least how to write the analysis proof or how to show something rigorously, okay? This would be very important, and well, I hope you can think about those kind of problems, when you try to do it in your homework or in the future, in the exams, you try to think about it, whether this step or that step is rigorous or not, in the sense of analysis. Okay, think about that. If it is not, then whether you think it is okay or not, whether you think it is, well, although it is not rigorous, not very rigorous, but it's understandable, it is fixable or not. At this moment, nothing for you guys can be understandable, I should say. Nothing for you guys can be ignored. So which means you have to think everything and write everything. It's better for you to write it in the sense of epsilon delta language, but it's fine if you don't write it like that. In the future, it might be okay for you to try to think about some problems and do something kind of a little bit weak and not very rigorous. But still, you have to know how to do it rigorous, okay? If you are, as long as you are familiar with this kind of language and tools for in analysis. So this is just my comment. And now let's see the problem. The problem is, we ask you to show this little L2 space is actually a complete space, which means, what's the meaning of a complete space? A complete metric space or a complete norm space. It just means that all the Cauchy sequence of this space converge to some element in this space. Okay, so this means two things. First, all the Cauchy sequence will converge. Okay, first thing, the Cauchy sequence will converge. And another thing is, it will converge to something, some element in this space. Okay? So let's try to show it is complete, which means you try to find a limit for the Cauchy sequence on this space. So let's say a K is a Cauchy sequence on little L2 space. It's a K n. And from 1 to infinity. Well, now you have to have two index for your sequence because well, it's a sequence of sequence. So you have two indexes. And then for each fixed K, it is a L2, it is a little L2 sequence. Okay? And a K is a Cauchy sequence in little L2Z. That is, for any epsilon greater than 0, there exists some kind of capital N such that if your KL is greater than capital N, a K minus a L with little L2 norm, let's denote this kind of norm by this footmark, by this well, subscript, okay, is less than epsilon. This is the meaning of Cauchy sequence of a normed space, okay? And we want to find the limit of AK. And we want to show that this limit is actually another element on L2Z. Okay? So this is very important. So first, let's try to find the candidate for the limit of AK. Okay? So if you have this kind of AK, then I think this step, most of you did it correctly, which is, okay, you have this AK. Then we know that, okay, this kind of thing is less than epsilon. So that means AKN is actually a Cauchy sequence for any fixed n. For any fixed n. Okay, so if you let K to change, then, well, componently, you can see that something like AKN, this is, well, AK1, and this, oh, well, I mean, A1N, and you have A2N, this is A1, this is A2, and this is A3, A3N at the nth position. Componently, if you see that vertically, you find that this kind of sequence, this sequence A1 and A2 and A3 and so on, forms a Cauchy sequence in C. Okay? Why is that? It's just because, well, a kn minus a ln, the norm of it is less or equal than, well, the summation of everything, and you take the square root of it, right? It's less or equal than a k minus al with the norm in L2. You just take one, well, you just take one term on this summation. AK minus AL in L2 of Z is equals to the summation in N, right? AK, well, let's not use N here, let's use M here to be different from this fixed N. AKM minus ALM. You take the summation of the square root and you take the, well, you take the square root of it. Okay, you take the sum in M. And of course, it's, well, it's greater or equal than, you just take one of them and let others equals to 0, which is why this must be true for this fixed N. Okay? That okay? So you know that there exists something which is a complex number such that if you take the limit in K is equals to Bn. Okay, for any n, there exists some kind of Bn, and if you take the limit in K, if you go this way, then eventually it will be very, very close to some number. We call this number Bn. Okay, so componently, you have a limit. Now the question is, if we call this sequence Bn to be B, okay, and from 1 to infinity, this should be the limit. You cannot have any other limit as a limit. This should be the limit of AK. But is it really the limit of AK as a sequence? And is it with little L2 of Z? This will become the problems we need to answer. Okay, this will become the problem. If both of them are true, then we can say that, okay, all the Cauchy sequence, because we choose a Cauchy sequence arbitrarily, randomly, has a limit, and this limit is in your L2. Then the L2, little L2 is a complete space. Okay? Any question? Any questions so far? So the only thing we need to do is we need to find whether this B is in little L2 or not, and whether you can say it is a limit. So, well, in order to do that, well, let's try to look at this term, okay? How we can show this B is actually the limit by using this kind of condition. This AK is a Cauchy sequence. So let's show it this way, okay? You have this AK minus AL for any epsilon greater than 0, there exists a capital N such that KL is greater than capital N, we have is less than this epsilon. Okay, so that means the summation of M, well, all this kind of N, or this kind of, let's take the summation of N because well, we just use this as an index, so it doesn't matter. AKN minus ALN square is less than epsilon square. We take square both sides. Okay, this is this one. So we take square both sides, then it becomes this one. Okay, and there are infinite many terms, so which means it's a little bit hard for us to take some kind of limit or try to do some analysis. So that means for any capital M greater than 0, we have the summation of N is less or equal than this M. AKN minus ALN square is less than epsilon square. We just take a partial sum of it. Then the total sum is less than epsilon square. Then of course this partial sum is still is even less than this total sum. It's still less than epsilon square. Okay, but now the good thing here is we only have finite many terms and take the summation, right? So which means what we can do is we can now take L goes to infinity. Okay, so this means you will have this ALN. We know that for any ALN, if you take L goes to infinity, what you get is Bn, right? So the summation, you only have finite many terms, so you can take this limit well freely. It doesn't matter. AKN minus Bn square is less than epsilon square. Okay? For any M, this is true. Okay? So that means, okay, for any M, you will have N is less or equal than M Bn square. If you take the norm of this kind of thing, by triangle inequality, you will get the summation of, or the norm of An. If you take the partial sum instead of the total sum, it's still some kind of norm, but it becomes a partial sum of norm. N is less or equal than M. Okay, this would be AKN. You take square and you take half power of it, plus this kind of thing. N is less or equal than M. AKN minus Bn square, and you take the half power of it. This is the triangle inequality for for the finite norm. Let's say it's finite norm, or the norm on Rn. Okay, and you know that, so that means if you take the partial sum of Bn square of this half power, is less or equal than this AK's norm, AK's related to L2 norm. This is only finite many terms. You take this L2 norm, then of course it's less or equal than the total sum. Okay, and plus epsilon square for any M greater than 0. Okay, so that means, okay, well, you know that this AK is a Cauchy sequence. So which means AK must be bounded above. Okay, you have shown that when you introduce this Cauchy sequence, I think. So which means AK in L2 norm is bounded above by some upper bound B. So we know that the summation of N is less or equal than M Bn squared with power half is less or equal than B plus epsilon square. Epsilon is some small number, so we can initially choose epsilon is 1 or whatever, then you know that B, if you take M to be bigger and bigger and bigger, you know that B, this sequence is in little L2 of Z. Okay? And moreover, you can see that this kind of AK minus B in little L2 norm, it is also less than epsilon. Okay? If you take M goes to infinity and see this part, it will be smaller than epsilon for K big enough. K is bigger than this capital M. So we have the limit of AK as K goes to infinity equals to B in little L2 of Z. Okay, so you have proved that any Cauchy sequence have a limit, and this limit is in little L2. Okay, any question? Any question? Any question? Okay, if no question, then let's continue and discuss the problem number 4. Okay, this problem. For this problem, I just want you to again make sure that every step you're trying to do is something makes sense. Okay, it has to be something makes sense, and it has to be something rigorous, not something.
I think we only have like half an hour left for the class, right? And we have a lot of problems.
Not really. Some of the problem you are really doing well. So I just tell you, this part is something very important because well, it just tells you you have to do everything rigorously. Okay, and the rest of the problem is just something you need to try to rethink about. Well, the proof you done. Okay, so it's not very hard. We will have time. Okay, you have any other question?
No, I was just worried we wouldn't be able to cover a lot of other problems.
It's okay, it's okay. Yeah, because for the rest of the problem, I can see that most of you got the idea or are able to get the idea. So it's okay. So for instance, for problem number 4, this problem, he said that, okay, if F's norm is equals to this kind of norm, okay, 1 over 2 pi, 0 to 2 pi, fx squared dx with power 1/2. Okay, and he wants you to show that f equals to 0, but f is not it's not identically equals to 0. Well, this is very easy, and most of you know that and able to write it. For instance, fx could be something that is 0, but only except at one point, right? X equals to 0, x not equals to 0 is equals to 2 pi or whatever, right? And if you only change 1 point's value of fx, then you got something which integral equals to 0. That's okay. The only thing I want to mention is part B. Okay, for part C, it's actually a little bit beyond what you have learned, and I think I made some mistake when I try to assign it. But for part C, is something a little bit beyond because it may need some kind of idea about the measure of a set. Okay, well, for part C, it just says that if a function is integrable, then all the point that for this function that is not continuous must be measure 0, which means it's almost everywhere continuous. But of course, you don't know what's the meaning of measure, and you don't know what's the meaning of measure 0 or almost everywhere. So we will just ignore this kind of thing and just say that, okay, if fx is integrable, and then it will be almost everywhere. It will be, in most of the point, it will be continuous. Okay, so for part C, we will just ignore it. The only thing I want to mention is part B. F is integrable, and f equals to 0. I want to imply that fx equals to 0 whenever f is continuous. at x. Okay, we want to show this. Well, I think most of you got the idea about it, but it seems that in real analysis course you haven't talked about it. So which is why you just say something about that but didn't write it in a rigorous way. Okay, that is when you try to say this kind of thing, you use those kind of so-called conservation of sign at point of continuity of a function. This kind of property, so-called this kind of thing. Conservation of sign, which is, if not, everybody know how to prove it, well, at least how to start it. If not, okay, then there exists something like x0 such that fx is continuous at x0. So we assume that f equals to 0, the norm of f equals to 0. Fx is continuous at x0 and fx0 is not equals to 0. Okay, then we want to get a contradiction. This is how we try to prove. Okay, so we can say that, okay, fx0 is equals to some constant c, and without loss of generality, let's say it's greater than 0. It doesn't matter. Okay, if it is less than 0, it still gets something, well, to be f squared is still something to be positive. And then the trick here is, since f is continuous at x0, what does that mean? That means some of you say that f should be something non-zero in some interval, okay? But that's not quite what we want. This is something a little bit tricky, which is why we somehow use it again and again in the future. That is, f is continuous at x0. That means for any epsilon greater than 0, there exists some delta such that fx minus fx0 is less than epsilon whenever x minus x0 is less than delta. Okay, this is a definition of fx is continuous at x0. Okay, and the trick here is, now if we choose epsilon to be some very specific number, for instance, a half c, then we plug in, what we find is, then there exists some delta such that fx minus fx0, which is c, is less than half c. Okay? Half c is your epsilon. That means fx is greater than half c, less than 3 half c. Whenever x is on the interval x0 minus delta, x0 plus delta. Okay? That clear? I think it's clear. Okay? So, what does that mean? That means on the interval x0 minus delta, x0 plus delta, we have fx is greater or equal than half c. So the norm of f, which is equals to 1 over 2 pi 0 to 2 pi fx squared dx with power a half, is greater or equal than, we try to release this upper and lower bound to be x0 minus delta, x0 plus delta, fx squared dx 1/2, right? This for sure is true because this is some interval that inside of this 0 to 2 pi. It's a very small interval, but still some interval. Okay, and you know that on this interval, your fx is always greater than half c. So this is greater or equal than, well, c squared over 2 over 4, and the total length of this interval is 2 delta. So what you will get is c squared over 4, 1/2 pi, well, 1 over 2 pi times 2 delta with power half. Okay, so which equals to, well, this would be c times delta over pi to the power half, which is a strictly positive number. Okay, this is a contradiction. Okay, so this is how you show this kind of problems in a rigorous way, which is very important. And you have to tell me not by some intuition, but by something concrete for this kind of problem. Okay. Any question?
I think by using the Parseval's identity,
yes, definitely. You can also use a Parseval identity for these problems, which is some benefit we can get from this well, Fourier analysis, which is, you know that, okay, if we already got the theorem say that, okay, the norm of this f is equals to the summation of an squared. And if the norm of f is equals to 0, then that means all the an equals to 0. And by our theorems we learned before, we got then f must equals to 0 at any point of continuity. That's totally true. Yeah, if you use that theorem, so you are doing correct. But what I'm saying here is you just make sure that if you try to use this kind of way, because I see some of you use this kind of way, then you have to be very careful and rigorous. Okay? Not something by intuition. Any other question? If no questions, then let's discuss problem number 6. Okay? For problem number 6, this problem I will not go to the details, but just to say something. Well, so he gives you a sequence AK and say that, okay, this sequence we can see that it's in little L2, but it is not the Fourier transform or the Fourier coefficients of any integrable function, which means L2 has more element than the integrable function. Okay, and the hint I gave you is, well, you can try to think if there exists some kind of functions with the Fourier coefficient equals to AK, then what we will find is f will, with Abel sums of the Fourier coefficient of it, of the Fourier sequence of it, it is not bounded above. Okay, I think most of you get how you can show it's not bounded above by saying that, okay, it's actually 1 over k and r to the power k and e to the in theta, right? This kind of summation. And this kind of thing is not bounded above. You can actually find what is, well, what is summation of this kind of thing. What is the summation when theta equals to 0, then the summation is summable. You can find it. You can use it like 1 over k x to the power k, and as long as you know how to find the summation of this, k is greater or equal than 1, as long as you know how to find this, it's actually, well, the derivative of summation of x to the power k, I guess maybe 1 over x something. You take derivative, okay? Or is x times it, something like this. Yeah, well, I don't want to do the algebra, but it's something like this. So you know how to take this derivative, how to take this sum is 1 over 1 minus x, and then you do some derivative, and you say that, okay, when x is less than 1, you always get this is true. So which means when theta equals to 0 and r is less than 1, you got this kind of summation, and when r tends to 1, yeah, it's unbounded. That's totally fine. I just want to say, okay, then what is the logic here? The logic is, although you know that f convolute with PR theta is unbounded, but that doesn't mean anything, right? It's unbounded. However, the contradiction we can get is this is unbounded. But if f is an integrable function, then what we should get is this is a bounded function. Okay, this should be a bounded function instead of an unbounded function. As long as you have a function, that is integrable, then you will get a contradiction. Okay, it's not because, well, this kind of functions, this kind of convolutions will converge to f at any point of continuous, and this is unbounded then, so that this kind of f is not, it does not exist. It's simply because this reason, not anything else. Not you really get some formula of f, because you don't know whether f is continuous or not. You just know, if you just know f is integrable, then how can you get something contradiction? You get contradiction like this, okay? You don't get contradiction by saying that, okay, you find a function that has this, well, the corresponding this Fourier coefficient, and then you find this function is not integrable. That's not enough, because what if we have some other functions which is not really like this, this kind of summation, which is not really like what you have, like this, have this kind of expression. Then the contradiction is, well, you must have this convolution to be bounded above. Okay, but you find that this convolution for your functions and this Poisson kernel is not really bounded above. Then you got a contradiction, which means your f does not exist. You don't have an integrable function. Okay, so this is about the logic I want to mention. Any question? And well, next question I would like to mention a little bit is problem number 19. Yes, the problem number 19 and well, the problem 2. This is exercise number 19 and problem 2 are the only two problems I would like to mention for today. Okay. And other than this, I just see that everybody doing well, so I don't really want to discuss more about that. It's just some computation. Okay. So let's first see, well, this problem number 19. Okay, this problem number 19 just say that, okay, we want you to show this kind of sum is uniformly bounded without using that Dirichlet criteria. Okay, it's kind of n is less or equal than n greater than 0, e to the in x divided by n. Yes, it's uniformly bounded. And you have already shown this by the previous homework, right? Because this kind of thing is uniformly bounded, 1 over n tends to 0, so it will be uniform bounded. It will actually converge, right? But here he gives you another idea about how you can show this is actually bounded above, okay? Which is he try to write it as the summation of sine nx over n, and from 1 to capital N. And you can write it as the, well, 1/2 of the integral from 0 to x, the Dirichlet kernel minus 1 dx. So if you want to show this this function is bounded above, then what you're trying to say is you want to show this function is bounded above. Okay, so now the question is how you can show this function to be bounded above. This is something I think most of you are able to do it by some similar idea on exercise 12, which is you try to do a computation from 0 to infinity sine x over x dx, and it's actually equals to 1/2 pi. Okay, you did an estimate about this this integral, and then you try to use some similar idea to say that this function, because it's a function in X, is bounded above. Okay. So how can we solve this problem? I think most of you get the idea. So basically what we're trying to show is you take the integral from 0 to x, and this dnx is sine n plus 1/2 t divided by sine 1/2 t dt. And you're trying to show that this function, because the other part of this function is just a -1, right? -1 is equals to, well, x. And x is bounded above when x is in minus pi to pi. It's bounded above. So the only problem now is how you can show this kind of integration is bounded above. Okay, how you can show it is bounded above, it is uniformly bounded no matter what capital N and what x you gave me. Okay, this is the only problem. So most of you try to do it this way, which is, well, let's fix x. And then let's try to take n goes to infinity and see what happens. If you try to take n goes to infinity, what you will find is, okay, this kind of thing will tends to half pi by the similar argument as x is 12. Okay, it's almost the same argument as x is 12. You just split it into different part, and then eventually you got it tends to half pi. That's fine, but then that doesn't mean that, well, in order to say that rigorously in analysis, that doesn't mean that this function is is bounded, well, it's bounded uniformly, which means regardless in x and n. What you have shown is when x fixed and n goes to infinity, it is bounded above. But you didn't say this function is bounded above, right? So if you want to show this function is bounded above, you need one more step. One more step. What is that? Anybody have any idea about how you can show it's actually bounded uniformly in x and n? How you can show this?
Riemann-Lebesgue lemma.
Well, Riemann-Lebesgue lemma is only true for n goes to infinity, right? Riemann-Lebesgue lemma only true for n goes to infinity. That's fine, you already use it here. But my question is, how can you show that it's bounded above in both x and n? How you can show this kind of statement? How can you say that rigorously? Because you only say that, okay, when n goes to infinity, it tends to a constant. But that doesn't mean that this kind of thing is bounded above in x and n. How can you make your argument rigorously? How can you make your argument rigorously? For instance, why we cannot get some kind of n and x, so, nj and xk, such that along this nj and xk, you get something unbounded? Why is that impossible? Well, why is that impossible? Or how can you use this limit to show that, okay, this thing is bounded about by some constant? How can you show this? Because this is what you want to show, right? This is what you want to prove. Well,
sorry, Professor, but I don't understand why Riemann-Lebesgue lemma is not enough, because if we know that when n goes to infinity, this is bounded above, then of course this is bounded uniformly, like bounded above by some constant, at least in n.
yes, so this is very important, and you have to say this, right? If you know a sequence which well tends to some limit, then this sequence is uniformly bounded, right? This you have to say. This is something you have to say, which is, you know that the limit for fixed x, the limit of n goes to infinity, this 0 to x sine n plus a half t divided by sine half t dt is equals to a half pi. This, well, let's say this is a function of fx equal to n, okay? You know when limit as n goes to infinity, fxn is equals to a half pi, then you want to conclude that fxn for fixed x is bounded above. Okay? This is simply because you have a limit. The limit, you have a limit, then of course you will have an upper bound. Okay? And also, you have a limit, you have an upper bound, you will also need to say that this upper bound is actually uniform in x. So which means for this limit, you have is equals to half pi. That's for sure. Okay, that's for sure to be true. And then what you need to say is, well, what you can show is, then that means capital Fxn is bounded about by some constant that may depend on x. Why independent in x? You have to say that, right? Why this kind of thing is independent in x? So you will get some upper bound that may depend on x. But then you will need to say again why Cx is bounded about by some other constant C. This would be another thing that is very important, right? So if you calculate it very carefully, then, well, this is actually something very easy to see. That is, this function divided by sine half t and dt, right? This function it tends to a half pi when you fix x. And then what you can say is, then this function is bounded about by something like from 0 to n plus, well, nx, I think. Something like sine x over sine t over t dt. And plus something uniformly bounded. If you do this kind of thing very carefully, it's bounded about by something uniformly bounded. So which means it's bounded by some other constant that may not depend on x. But of course you have to say this. Okay, you have to be very carefully to say this kind of thing. Otherwise, it is not very explicit. It is not very rigorous. Okay. Okay. Any question about this part? Well, I just want to mention this. That is, when you try to say some function is bounded above, when you try to say fxn is bounded above, you only take one limit that may not be the whole problem. You may need to consider more. Think about, okay, you have a function of two variables, fx, y. You know that for any x, if you take y goes to infinity, this function has a limit. But does that mean that this fxy is bounded above? At least you need to say that. At least you need some other argument on this function. For instance, this function is continuous in x, and this function is continuous in y, actually smooth in x and smooth in y, then probably it's okay, right? Probably it's okay to say that, okay, this function, if it has a limit, then this function is actually bounded above. For instance, you know this function, when you take x goes to infinity, then this function has a value, then that means when x is very big, this function is bounded. And when x is very small, it's not so big, it's on a bounded domain, right? It's on the bounded domain, and well, a continuous function could have an upper bound and lower bound. It's bounded above and below. So if a continuous function as x goes to infinity, it is finite, we can conclude that this function is bounded above. Okay, but you still need this continuity of this function. Otherwise, it might not be true. So you need this kind of argument to complete your visualization, okay, which is very important. And well, this is something I would like to say about this problem. And well, the argument is kind of routine, and I think you are able to argue it. It's fine, because from what you write, I think you basically got the idea. You just need to be very careful step by step. Last thing, in 3 minutes, I would like to just say a little bit about this Laurent formula and this Laurent polynomial. Okay, it's an nth power polynomial, and you want to show that this Laurent polynomial also forms an orthogonal family, or some kind of orthogonal basis of your continuous function. Okay, and this problem itself is not very hard. You just need to do some calculation, and this calculation is very tedious, and I'll just say a little bit about this kind of calculation. For instance, for A, he wants you to show that you take the integral of this Laurent polynomial, and it's equals to -1 to the power n, and you can do the integration by part n times and make this derivative to f. Okay. Well, this is the only thing this problem you just need to be careful about. Okay, for this Laurent polynomial, you can write it as d over dxn, x minus 1 to the power n, x plus 1 to the power n. Okay, so you have to distribute this nth derivative to this n, x minus 1 to the power n, and x plus 1 to the power n. And you will find that then, in that case, well, on the boundary of 1 and -1, you always get some 0. Okay, you always get some 0, so which means the boundary value or the integration by parts, this not integral part will disappear, will always disappear when you take this derivative less than n. Okay, so which is why you can move this derivative to this f. And for part B, he wants you to take this ln norm and show it's actually a constant. And this constant is very explicit, which is also very ugly. This one squared 2 to the power 2m plus 1 divided by 2m plus 1. Okay, and he gives you a hint and say that, okay, basically you can first try to do some integration by parts. this integration by part is almost the same as what we did here, but it's actually the integration by part of x squared minus 1 to the power n dn dxn x squared minus 1 to the power n dx, right? And you try to move this n derivative to here, because this is a good function. This can be seen as f. If you move it here, then you take the 2n's derivative of this 2n's polynomial. Then of course you get nothing but only the highest power times the derivative to 2n times. Okay, so which is why you must have, after the integration by part is minus 1 to the power n times 2n factorial and x squared minus 1 to the power n minus 1 to 1 dx. Okay, and then the only thing is you have to find the antiderivative of this kind of polynomial, which is very ugly, but you can always do it like change of variable, for instance. This is x minus 1 to the power n times x plus 1 to the power n. So if you do a change of variable, it might be something like x to the power n times x plus 2 to the power n dx, right? And then you can try to do another integration by part to try to put this x to the power n inside of this one. And then as long as you take the derivative of this, you get x to some higher and higher and higher and higher power. So eventually you are able to remove all the power of x plus 2 to the power n to x to the power 2n. And then you know how to find the antiderivative, then you got the final answer. Okay? And for the last two parts, for this orthogonality of this Lagrange polynomial, I will refer you, for instance, for the Gram-Schmidt process, I'll refer you to Google it. You can find there is a web page where there is a stock exchange website, and you can find someone asked some similar questions, which is how you can see this Lagrange polynomial as the Gram-Schmidt process of the polynomial, how you can see it like that. And if you will, then what you need to do is you just need to follow this kind of answer. And the way you try to see it is very simple. You just try to see, okay, this Lagrange polynomial has some relation with Ln minus 1 and Ln minus 2. And you find that if you try to do the Gram-Schmidt, maybe some of you do not know what the Gram-Schmidt means, so you can Google it again. Then you find that the Gram-Schmidt you get from this polynomials 1, x to the power 1 and x squared has also the same propositions, have the same relations as this. Okay, something. And then, so if you want to show that Ln is the same thing as you did for the Gram-Schmidt of x to the power n, you just need to check whether L1 and L0 and L1 coincide with this Pn, P0 and P1. That's enough. Okay, this is how you do D. Well, for C, maybe I should mention one more thing. For C, how you can show this x to the power n is orthogonal to this Ln, or how you can say this kind of thing is true. You can just will write those kind of polynomial Pn as a linear combination of Ln. Okay, and then you can find that, okay, then will eventually you must have this Am to be non-zero, Ak to be non-zero, and you can find the expression of it. Sorry, I make it a little bit late, but for this part is the Lagrange polynomial. You can really search a lot of things from the internet and you can really find everything. And I set it as assignment simply because I think this is something very useful for in the future, because maybe some of you may need this kind of thing to really solve some problems. And but for this part, I'm not really interested, because in the sense of analysis, It's not that interesting because it's kind of, well, you have to do a lot of calculation like this, which means it's kind of very ugly, okay? So which is why I don't really want to mention too much about it. But of course, if you have any questions about this part, feel free to ask me, okay? Sorry for the delaying of our course, but that's all I want to discuss and for today. And if you have any other questions, I will be here until 6 o'clock, okay?